Hello everyone, this video is going to walk through worksheet 3 of our circular motion packet so that you can get started on each problem. If you need to see full solutions, be sure to refer to the solutions posted in Schoology. So for question 1, we have the passenger that's inside the airplane, which would be located right about where that star is, and the passenger would be upside down. So drawing a force diagram for this problem to start off. Here's our passenger, and we have two forces, force due to gravity and normal force acting on the woman flying the plane. Now, we don't know which force is larger. As of yet, I just drew them both relatively what I would initially think. So to solve for we have to make a quantitative force diagram, so we're going to need to solve for force due to gravity and normal force. So we have the mass of the pilot, so Fg equals mg, so we could see that the pilot weighs approximately 550 newtons. I'm just going to move this to the other side here. And then we can start the rest of our problem. Where centripetal force, or the net force for circles, is mv squared over r. Our centripetal force is made up of two forces, force due to gravity and normal force. And I'm going to call down positive, that way I don't have to worry about any other sign. So if I call down or towards the center of my circle positive, then everything is positive. So I have my weight of my passenger. I'm going to solve for my normal force. I know the mass of the passenger, the velocity of the plane, which I'm going to need to convert this to meters per second. So I'm going to leave that for you to solve. And I know my radius of 380 meters. So go ahead and make sure you convert that velocity from kilometers per hour to meters per second, and then you could solve for normal force. For number 2, we have a track where students of differing masses are running around different lanes of a track. Question A is asking us to look at the centripetal acceleration of each child. So centripetal acceleration is just that v squared over r of our equation that we developed last week. And part B is asking us to look at the whole centripetal force. So we're going to use the full equation. Now going back to centripetal acceleration, notice that, let's see, everybody is running with equal speeds. So my velocity is going to be the same for each child. So really I'm looking at the proportion of centripetal acceleration, or rather inverse relationship of radius and acceleration. So if you go through, say for example, the students that are running in the first lane where it's a radius of 4r, their reference acceleration would be 1/4. Then the athletes on the second lane would be 1/5, and so on. So you can use that to rank the centripetal acceleration of each athlete using just the radius as a reference. For part B, again, we're still looking at velocity being the same. So that's not going to impact our rankings. So it's going to be the proportion of mass and radius. So what I would do for, say, athlete A, they have a radius of 4m, so I'm going to say 4, because it's 4 times m, and a radius of 4. So mass of 4, radius of 4, an overall value of 1. So then I might go for, say, athlete D. Doing the same thing. It's going to be mass, the proportion of mass over radius. So twice the mass, radius of 4, an overall value of 1/2. And then you could do that for each lettered athlete and then compare them at the end. Number 3, we're going to skip for a few reasons and go to question 4. So we have Tarzan. Tarzan's going to swing on the vine. And at this location, the branch kind of shortens the a radius of the swing, and we need to see what happens. So first we want to sketch out a force diagram, and I know it's going to be for part B, but the conception for A is that as the radius decreases, the tension would have to increase. And so I'm going to draw my force diagram on the side here, but I'm drawing it for at position B. So at position B, we have force to gravity and tension, where tension needs to be larger because he's swinging in this circular turn. So if he has a mass of 80 kilograms, he is approximately 800 newtons. And we're going to solve for Ft. So we have our circular motion equation, where the forces involved here are gravity, which I'm going to call down, or outside of my circle, and normal force going inward or up, positive. So I know Fg. I'm going to solve for F. Oh, I called it Fn. It's Ft. Or this would be the grip strength that Tarzan or the person would have to use. So we have Fg. We're solving for force T. We know mass. We know velocity. And we know radius. So you go ahead and solve for Ft. For part C, this is when the vine radius changes. So we're just going to go ahead and recalculate the tension force with that smaller radius. For part 5, or question 5, this is very similar to our other track question where we're just looking at ratios. This time we have equal masses of athletes. So for our centripetal acceleration part A, we're going to be looking both the velocity and the radius. So for, say, athlete A, a relative velocity of 4, but 4 squared, over that radius of that lane is 4. So pretty easy math. We got an overall value of 4. So then, say, for athlete F, relative velocity of 2 squared, and in the outside lane of 6, so we would say 4/6, or overall value of 2/3 for our ranking purposes. For part B, again, we're looking at centripetal force, where the masses are the same. So we're looking at this kind of proportion of V squared over R, which you'll notice it's going to be the same as part A with the centripetal acceleration, because the masses are no longer relevant because they're all equal. And finally, question 6. We have this ride where the passenger kind of sticks to the wall and goes around in circles. So for purposes of my force diagram, I'm going to show where the passenger is on the left side. So while the passenger is spinning, we have force due to gravity down, and it's going to be friction that's preventing the passenger from sliding down. And they're going to be equal, and our centripetal force pointing towards the center of the circle is the normal force caused by the wall. So we're asked to find the period of rotation. Period of rotation is just the time needed to go one revolution. And that's going to be hidden, so our final answer, in our velocity. So we're solving for velocity, for velocity, where the distance traveled is circular. So it's the circumference of the circle, so 2 pi r over, I'm going to put a capital T because that's a symbol for period. So that's going to be my overall goal, is to solve for this T. But then going back to the problem, right, my one force that's causing my circular motion in this problem is normal force. But I don't know what the normal force is. And I don't know a specific equation for normal force. But the one equation that I do know that has normal force in it is the friction equation. So I can rearrange that to say normal force is equal to force of friction over mu. So that helps me out. So right now I could calculate the normal force because I do have some values here. I do know that force of friction is equal to gravity. And I know the mass of the passenger, so I know that is around 730 newtons. But I want to continue further to just kind of show you something. So force of friction, we just stated, is equal to gravity. And the equation for force due to gravity is mg. So that's over mu. I'm just continuing with my derivation. And I see that mass cancels out. So the mass doesn't really matter, which is why when you ride amusement park rides like this, they're not weighing people as they get on just to see if they would actually be able to not fall down as the floor drops out. So I have g, I have mu, I have radius. So I could solve for velocity, not forgetting the squares there. Take that velocity and then solve for the time. And again, be sure to refer to the solutions in Schoology in full if you need to see step-by-steps.